All right, we're going to start talking about the uniform circular motion problems. Number one, a runner moving at a speed of 8.8 meters per second rounds a bend with a radius of 25 meters. We want to know, what is the centripetal acceleration of the runner? First thing we're going to do with all of these problems is any numbers we're given, like 8.8 meters per second and 25 meters, we're going to pull those out and write those down. So here they are for number one. The velocity or speed is 8.8 meters per second, and the radius was 25 meters, and the question was asking for the acceleration. So I look at my equation sheet, and I say, all right, which equation has a in it, and also has the things I'm looking for? Well, that would be the a equals v squared over r equation. That's the one I'm going to use because it's got the v, it's got the r, I can easily plug in. So 8.8 squared divided by 25 meters, and that's going to give me an acceleration of 3.1 meters per second squared for the runner going around this track. Now I'll take a look at number two. Number two, a car going 32 meters per second rounds a curve with a 56 meter radius. What is the car's centripetal acceleration, and what would be the minimum coefficient of static friction necessary between the tires and the road before the car would start to slide? Especially for some of these ones with stars, you might want to draw a picture. It'll help you out a little bit. So here's my overhead view, my Google Maps view, or Google Earth view of what the heck is going on with this car. So you got cars going around a turn. The force that holds the car in place is the force of friction. Because if it was snowing, that's when the car would start to slide off and might end up in a ditch over here or something. So the friction is my centripetal force. So that's why I wrote right here, friction equals centripetal force. They are the same thing. And then if I was a car behind this car, the forces I would see on it are gravity down, the normal force goes up, and friction is pointing towards the center of the circle. The numbers I was given in the problem, v equals 32 meters per second. That's how fast it was going. The radius of the turn is 56 meters. It wants to know the acceleration, and it wants to know this coefficient of friction. So first things first, let's find the acceleration. I have v, I have r. This is just like the previous problem where I look for an equation that's got the thing I want, a, and the two variables I've got, v and r. I can plug in my numbers, 32 meters per second. I square that, divided by 56, and I get an acceleration of 18.3 meters per second squared. Now here's the trickier part, which is how do I find that coefficient of friction? We still only have one equation for the coefficient of friction, and that is mu times the normal force. So friction is the centripetal force, and friction is mu f of n. Now over here, I can use any equation that I have on my equation sheet that talks about the centripetal force, because the centripetal force is friction. So all of those equations for centripetal force are describing friction. So I can pick whichever one I want. I'm going to pick the first one, which is just ma, because I have the acceleration. We just solved for it. So I have mu times the normal force equals ma. Well, now the normal force is right here. Gravity is down. This is a nice flat road. So normal up equals gravity down. So where I have normal force, I can just write gravity, and gravity is mg, mass times 9.8. So my equation becomes mu, nothing happened to that, times mg, because that's what the normal force is, equals ma. And if you look, I've got mass on both sides, so I can divide them and they cancel. That leaves me with mu times g equals a. I'm trying to solve for the mu, the coefficient of friction, so I'm just going to divide the g over, that's why it's in the denominator now, and I get a divided by g, which is 9.8, will give me the coefficient. So for mu, I'm going to have a, 18.3 meters per second squared, divided by 9.8 meters per second squared, and that gives me a coefficient of 1.87. So if I don't have that coefficient between my tires and the ground, I'm going to slide off the road. So if it's anything less than that, I'm going to slide off into the distance and end up in a ditch on the side. All right, let's take a look at number three. All right, number three, how long does it take a plane traveling at a constant speed of 110 meters per second to fly once around a circle whose radius is 2,850 meters? Again, we're going to pull our numbers out. The velocity was given at 110 meters per second. The radius was given at 2,850 meters, and it wants to know how long this is going to take. I look to my equation sheet and say, what equations do I have to work with? And I have v equals 2 pi r over time, the speed equation for this, because it's got v, which I have, r, which I have, and it's got time, which I want. So I'm going to rearrange this equation a little bit to solve for time. So I multiply time up to the left, and divide velocity back over to the right, which is why velocity is now in the denominator here. And I can plug in my numbers. 2 times pi times the r, 2,850 meters, divided by my v, 110 meters per second, gives me a time of 162.8 seconds for this plane to go around this circle. Now we'll take a look at number 4. Number 4, a car travels at a constant speed around a circular track whose radius is 2,600 meters. The car goes once around the track in 360 seconds. What is the magnitude or size of the centripetal acceleration of the car? I pull out my numbers. The radius was 2,600 meters. The time was 360 seconds. I'm looking for acceleration. I look at my equation sheet and I say, which equation should I use? Well, I have an equation set up already for A. That is 4 pi squared r over t squared. And I have r, I have t, so that's the equation I want to use. Plugging in my numbers, 4 times pi squared times 2,600 meters, divided by the time, which is 360 seconds. Don't forget to square it. And when I do that, I get an acceleration of 0.79 meters per second squared. Last one we're going to do is number 5. Number 5, riders in a bobsled race travel down the track with a speed of 34 meters per second around a turn with a radius of 33 meters. Assuming the mass of the sled and riders is 350 kilograms, what is the centripetal force acting on them? What is the centripetal force if the turn is made sharper with a radius of 24 meters? That should say if, not is. Now we fixed it. Okay, so let's go to how we solved it. Number 5. The first part, the speed is 34 meters per second. The radius is 33 meters. The mass is 350 kilograms. And we want to know the centripetal force. So I looked at my equation sheet. What's my centripetal force equation, which has m and r and v in it? It's right here. Centripetal force equals mv squared over r. I plug in my numbers. Mass is 350 kilograms. V is 34 meters per second. Don't forget to square it. Divided by a radius of 33. I plug all my numbers in, and I get a centripetal force of 12,260.6 newtons, or this bobsled is not going to hold this turn. Now, what happens if we make the turn sharper? A smaller radius means a sharper turn. Well, I would still have the exact same equation. V is still 34, m is still 350. I've just changed my radius from 33 to 24, which is a sharper turn, and I can plug in my numbers. So my mass is 350 kilograms. My speed is 34 meters per second. Again, don't forget to square it. And I divide that by 24 meters. And that gives me a much larger centripetal force of 16,858.3 newtons, which means it takes a lot more force to hold you on a sharp turn than a much wider turn. And that's the end of number 5.